Welcome to the last of 5 lectures in Unit 6, Earth's Dynamic Atmosphere. This lecture will cover material from Chapter 20, the World Climates and Global Climate Change. Climate system is comprised of many different spheres, many different components, many different systems, and many different feedbacks. Climate, as we learned in Chapter 18, is an aggregate of weather. That is, it's generally viewed as average weather over long periods of time or large expanses of space. Space meaning superficial area on the global, on the Earth. Climate system is fundamentally characterized by exchange of energy and moisture between the various systems and spheres in the Earth system. The atmosphere, hydrosphere, solid Earth, biosphere, and a component of the hydrosphere called the cryosphere, which is the ice and snow system. World climates vary widely over space and time. Every location has a distinctive climate, and the most important elements in a climatic description of an area are temperature and precipitation. You can see the climatology of the United States, mean daily average temperature, shown in the upper left corner. You can see fairly intuitive. The southern regions are hot, the northern regions are cool in terms of temperature. And in the lower right hand panel we see a global average precipitation map over 12 years in the late 80s to mid 90s, 8 years. Again, you see patterns that you should be familiar with based on what we've learned about atmospheric circulation. That is, equatorial or low latitude temperatures tend to be warmer than high latitude, and low latitude precipitation bands are due to convergence around the equator due to atmospheric circulation patterns. When scientists talk about climate, they tend to, again, need to set up a vocabulary. It's a system of description for the various climate systems that exist. These distinctions are useful, but again, like all vocabularies, there's always going to be exceptions and variations to each set of rules. But the Köppen classification system for climates brings order to large quantities of information, and it's the best known amongst the climate classification system, and it uses or is based on mean monthly and annual values of temperature and precipitation to delineate various climatologies around the world. The good thing about the Köppen system is that it generates a useful number of climatic differences or climatic zones, but that aren't too many. So there's roughly 15 zones in the Köppen system, with variations in subzones and whatnot. But it breaks it up into a useful number of distinctions. Köppen classification is realistic in a sense that it divides up the climate systems into a useful way, useful that is for science and description. Boundaries are based on limits of certain plant associations. So it capitalizes or is based on the fact that biology tends to be climatically driven, especially biology that's not mobile. Plants are mobile on long time scales. That is, they can evolve and move over time, but they don't transport themselves, generally speaking, or intentionally transport themselves. They're the plankton of the terrestrial realm. 5 principal climate groups in the Köppen system are humid tropical, which is the A system, dry, the B system. C is humid mid-latitude with mild winters, and D is humid mid-latitude with severe winters, and then polar. So you can imagine, if you can actually envision the type of distinctive plants or distinctive productivity that would occur in each of these regions. They're fairly well defined. Anyone who has read a National Geographic or watched a nature show on PBS will have a general sense of what humid tropical versus dry would look like in terms of the plants that exist in those regions. The A, C, D, and E, that is all of the climate zones except for the dry, are defined on the basis of temperature, and precipitation is the primary criterion for the B group, that is the dry zone. On the right you see a general map of the Western Hemisphere and showing the different zones. And you'll also notice that there's the 13th one at the bottom, the Highland classification system. That's slightly that's H. That's not really shown or described here in the left classification. That's a slight kind of combination category that we'll get to at the end. So, going through the climate classification scheme, humid tropical climates, climate classification A. They're winterless, so they're in the tropics to subtropics. All have mean monthly temperatures, with all months, having a mean temperature above 18 degrees C. That is, it's not an average annual temperature above 18 degrees C, which you could encounter in a zone that had really, really, really warm summers and moderate winters. But these are zones where every month has a mean temperature above 18 degrees C, which is pretty warm. Two main types in the A system. They're wet tropics, and then there's tropical wet and dry, which has a seasonality to the rainfall. So wet tropics, high temperatures and year-round rainfall. Tropical rainforest is the characteristic, so you can imagine these with lush vegetation. There's a discontinuous belt of these wet tropics around the equator, again based on continental arrangements and orographic kind of rain shadow deserts are the things that interrupt these belts, or this belt. And it's influenced by or controlled by the location of the intertropical convergence zone. That is the equatorial low pressure zone of convergence that surrounds the globe. The other type, tropical wet and dry, the AW type, are relatively poleward of the wet tropics, and equatorward of the tropical deserts that occur in these kind of mid-latitude bands. They're characterized by tropical grassland, that is savanna, so they're not as luxuriant or lush in terms of vegetation. They're not tropical rainforests, and they have a seasonal rainfall instead of year-round. A-type climates exist around the globe, and this is 3 examples of the A climate zone. You can see the AF zone, which is wet all year on the left-hand panel. That's in Peru, which is on the windward side of the Andes Mountains. So orographic lifting, we're going to have lots of rainfall due to adiabatic cooling. You can see rainfall precipitation map in the blue bars down below has a relatively high amount of rainfall. There's really no kind of mode, or there's really no difference between one month to the next. They're all significant rainfall, and the temperature, as shown by the red line, tends to be stable year-round. It's equatorial conditions, wet and hot. The AM classification with a very, very short dry season is shown in the plot of Monrovia and Liberia, Western Africa. You saw a map in the last chapter that showed some pretty intense thunderstorm activity in that zone of the world. And this is, again, you can see that as evidenced in the June-July precipitation map. The dry season, January through March, on the lower, we're looking at B panel here, but in the zone of January through March, where precipitation bars are very low, is a relatively short dry season. And we have very high, elevated, but stable temperatures. And then a longer dry season, which is this AW, this tropical wet and dry, is characterized by Normantown, Australia, or analogous to, and it's an example of, where temperature does vary a little bit more than in the AF and AM zones, but again, the latitude, we're at 17 degrees south, whereas the Liberia and the Peru site are 4 degrees and 6 degrees north. So right on the equator, right on the ITCZ. Normantown, Australia is barely tropical. It's almost subtropical. So it has a little bit more seasonality to the temperature. That is, in wintertime, temperatures go down because the sun is dominantly heating the northern hemisphere. The rainfall pattern is intense rainfall in the winter months, which is the southern hemisphere summer. So in the January, February, March. And in the southern hemisphere winter, which is June, July through September, October, is relatively dry. Again, characteristic of this kind of multimodal or bimodal tropical wet and dry system. Dry climates are where evaporation, again, remember, dry climate, or the B class, is the only classification scheme where temperature is not the main or a main metric for classification. This is entirely based on precipitation or available water. So in dry climates, evaporation exceeds precipitation and there's a water deficit or water deficiency year-round. The boundary of these zones is determined by variables such as average annual precipitation, average annual temperature, and the seasonal distribution of precipitation. And again, we have arid or desert BW zones and semi-arid or steppe BS zones, which are based on humidity and temperature. Causes of deserts and steppes in low latitudes are generally orographic in nature. That is, they coincide with dry, stable, subsiding air on the backsides of high mountains in the mid-latitudes, and in the low latitudes, they correspond to the presence of dry, stable, subsiding air in the subtropical high-pressure divergent zones that cluster around 20 to 30 degrees north and south latitude. The various B-type climates in a plot similar to what we saw with the wet climates. BWH, which is desert, a low latitude desert. Cairo, Egypt, is characterized by very little precipitation year-round, very little, although there is a little bit of seasonality, but it's so negligible, and really intensely hot summers, relatively cooler but still warm winters. The steppe, which tends to surround deserts, again we're in this latitudinal band around 30 degrees north or south. We have a little bit more seasonality to rainfall. There actually is a intense rainfall season. I shouldn't say intense. There's a rainfall season where there's some rainfall. Grasslands predominate. In the northern hemisphere summer, those rains occur in June through September. And then a middle latitude desert such as Nevada. It's further to the north, so it's 40 degrees north. Rainfall is stable year-round with very, very little, and temperatures vary from very cold, almost freezing or sub-freezing, to relatively warm in the mid-80s to 90 degrees. Humid mid-latitude climates with mild winters, which are defined as C-type climates, are characterized by temperature. That is, average temperature of the coldest month is below 18 degrees C, but it's above -3, so it differentiates from polar climates. And you've got three main types. You've got humid subtropics, so we're in this 23 degree latitude band, so similar to the last plot we saw of the B type of the desert band, but this is a case where maritime tropical air masses tend to dominate. It tends to be on the eastern side of continents. In the mid latitude band of 25 to 40 degrees north, hot summers, mild winters due to proximity to coastal waters and the heat capacity of seas. And winter precipitation is generated along fronts. In the marine west coast environment, which is a CFB, tends to be on the western or windward side of continents. They tend to be slightly further north than the humid subtropics. Florida, or Peninsula Florida, is a humid subtropical climate, for those of you who want to know. But in the marine west coast are typical of the west coast of California, Pacific Northwest. You have an onshore flow of ocean air which brings moist air to a zone which keeps winters cool. Winters warmer than they would otherwise be and summers cooler than they otherwise be, and can bring a significant degree of moisture to the environment. And then there's dry summer subtropics, which are tend to be on the west side of continents in the southern hemisphere between latitudes 30 and 45. There's strong seasonality to rainfall. There's a winter rainfall maximum, which is the southern hemisphere winter is in May, June, July, August. It's often considered or called a Mediterranean climate, which is just basically a Eurocentric view of the climate system. Now, the fourth out of five major differentiations or major climate systems is the humid mid-latitude climates with severe winters. So the last was with mild winters, and those had temperatures lowest, coldest month is below 18 degrees C, but above -3. The mid-latitude climate with severe winters is where average temperature of the coldest month is below -3, so much cooler, and the warmest monthly mean exceeds 10. So you have this still mid-latitude seasonality. It's not polar where it's cold all the time. They are dominantly in interiors of continents, absent in the southern hemisphere. There's just not enough continental mass. And the two subzones or subclassifications are the DFA and DFC, which are humid continental, DFA, similar to Chicago, or Chicago, Illinois has this, where summertime temperatures are relatively warm, wintertime temperatures are very, very cold, but precipitation is generally greater in the summer than in the winter, but there's significant precipitation year-round. And then subarctic is north of the humid continental climate, like Chicago, often referred to as the taiga climate, and it's the largest stretch of continuous forests on Earth exist in these zones, these taiga forests in northern Asia and North America. They're the source regions of the continental polar air masses, and they are very, very deep cold in the winter, but quite temperate, warm, pleasant summers. And then polar. Polar climates are fairly intuitive. There's tundra and there's ice cap climate. Tundra climates are characterized, they're treeless, that's what defines tundra, almost exclusively in the northern hemisphere. There's just not enough land mass in the southern hemisphere, especially in the high latitudes, except for some areas of South America down near Patagonia. Severe winters, cool summers, high annual temperature range. That is, there's quite a lot of variation. In Point Barrow, Alaska, for instance, this tundra climate can vary between 40 degrees C and minus 22, 40 degrees F and minus 22 F. That's a huge range of temperatures, almost 60 degrees for such a northern latitude. And an ice cap climate is characterized by relatively stable precipitation. There's no it's permanent ice and snow. There is actual precipitation. I'm not sure why this graph doesn't show precipitation, because ice caps have precipitation, but there's no monthly temperature above 0 degrees C. This graphic shows an actual monthly temperature and average up in the 10 degrees C range. So this is borderline EF. Highland climates, which is kind of this catch-all phrase for it's kind of for these zones that oscillate between strict Köppen climate differentiations. As I said, not all systems of classification can be viewed as entirely finite and discrete. Yet there has to be, or the best classification schemes have some flexibility built in. And highland climates is where this interchangeability occurs. Usually cooler and wetter than adjacent lowlands, but climatic conditions can vary greatly between even desert steppe or water stressed areas to tundra and to hot tropical humid. Now this chapter kind of comes to a close with a discussion of the human impacts on global climate. Now it's a fairly controversial subject. A lot of people don't like to discuss it. We hear a lot about it in the political and cultural spheres. But humans have been modifying the environment over extensive areas for thousands of years by using fire. Fire consumes wood resources, and human beings have had the remarkable ability to change the landscape dramatically by burning wood for fuel, as well as clear-cutting areas for cultivation. And by domestication of animals and overgrazing of marginal lands. Marginal lands means lands that aren't able to sustain themselves when their resources are utilized by concentrated activity, grazing. Most hypotheses of climate change are politically and culturally controversial. That is, we hear a lot about them on the news shows. We hear people arguing about them, whether it's at Thanksgiving dinner and your liberal uncle is arguing with your conservative aunt about climate change and all sorts of other things. People tend to pigeonhole each other and in a way, unfortunately, pigeonhole themselves based on their political leanings. They tend to pigeonhole their opinions about climate change and their understanding of it based on those things. But the processes, causes, mechanisms of global climate change are overwhelmingly accepted by the scientists who actually study them. There is debate in climate change research circles, but it's usually over small details about how specifically things happen. There is virtually no debate. And as a scientist, I say virtually because as a scientist, I have to. I would never ever say anything is absolutely set in stone as fact. But there's virtually no debate about whether climate change is happening. Most scientists agree, or the vast majority of scientists agree, that climate change has always happened on the face of the earth. And there is no debate about the fact that climate change is being affected by human activities. Now, you may hear in the newspaper, you may read in the newspaper or hear on the news that there is no consensus, that scientists aren't agreed upon things about climate change, but that's really disingenuous, and that is factually untrue. Scientists who actually study this, and there are tens of thousands of scientists who study climate change and study the systems that are involved in the climate system, all virtually agree, or all agree, that climate change has happened in the Earth's past, that climate change will happen in the Earth's future, and that climate change is happening now. They also agree that the vast majority of carbon dioxide in the atmosphere over the last, or the vast majority of the increase in carbon dioxide over the last 150 years is due to human activity. Now, there is no judgment in those determinations. There is no judgment among scientists about whether whose fault it is or whether somebody should be blamed. The fact of the matter is that the amount of carbon dioxide in the atmosphere has increased dramatically when humans beings started using fossil fuels. And the fact of the matter is, and has been known for hundreds of years, that carbon dioxide is a greenhouse gas and does in fact cause atmospheric warming. Now, what to do about it, or whether anything should be done about it, that's a matter for politicians and human beings who vote. But to call into question the motivation of scientists and to call into question the actual science and to imply that the science is not there to support the conclusion that climate change is in fact happening is fundamentally ignorant or fundamentally dishonest. So, whatever your opinion about climate change is, and with whatever your opinion about what should be done about climate change, at least do yourself a favor and understand the fundamental science behind it. Global temperatures have increased over the last 150, 200 years. That's known based on actual people monitoring and recording the actual temperature at different places around the Earth. The balance of evidence, the vast majority of evidence, suggests that humans have had a profound impact on the amount of carbon dioxide in the atmosphere. This top right plot is a plot of carbon dioxide concentration in the atmosphere over the last 400,000 years. And you may wonder, how in the world do we know what the concentration of carbon dioxide in the atmosphere was 400,000 years ago, 300,000 years ago, even 200 years ago, before people had the ability to directly measure carbon dioxide? Well, the beauty of geology, and you know this from stratigraphy, is that layers of Earth material, as layers accumulate, they record signals of what transpired or what existed at that point in space and time. Ice cores, which accumulate over long periods of time in the ice caps, in the continental ice caps like Greenland or Antarctica, actually record or actually contain atmospheric gases. And scientists can measure atmospheric gas concentrations from 400, 300, 200, 150,000 years ago in ice cores. And so we see this plot of carbon dioxide concentrations through the years, starting at the 450,000 years ago here, moving toward today. These long cyclic swings in CO2 concentration correspond to the geologic record periods of glaciation in the northern hemisphere. And they actually correspond to orbital cycles, the Milankovitch periodicity of orbital variations in precession, eccentricity, and obliquity that physicists know and astronomers know to be fact. What we also know is that the concentration of carbon dioxide in the atmosphere since 1950 has gone from 280 parts per million to at 2010 it was at 391. Now it's actually at 400 ppm. If we could update this graph in 2012, it would be right up here at 400 ppm. What's interesting about the atmospheric concentration of CO2 is that there's a chemical signature, a chemical tracer called carbon-13 that scientists can use to figure out basically where that carbon dioxide came from. And it turns out that the carbon-13 signature, the fingerprint of that carbon dioxide in the atmosphere, matches exactly the fingerprint of oil or fossil fuels. So it's not a reasonable argument. In fact, it's just plain wrong to argue that scientists do not know where the carbon dioxide in the atmosphere has come from. They do, in fact, know conclusively that it has come from primarily from burning of fossil fuels. Now, another way of looking at climate change or temperature change on the Earth's surface is to look at what's called an anomaly. That is, looking at the temperature of a place relative to what it typically is. And this plot down here below is a plot of global average surface temperature plotted against the average. So if you were to take an average global temperature of over the last 2,000 or 3,000 years on the surface of the Earth, it would and mark it as 0 degrees C. This is not a real scale of temperature. This is marking it as an average at 0, and then measure and then record the average temperature of a place on Earth relative to its long-term average from 1850 to about 1978. You see that temperatures in general were below the long-term average. But here we have a period of time from 1980 and beyond where global temperatures are well above their long-term average, which suggests that in fact global temperatures are rising and actually rising fast. Now, warming trends over the surface of the Earth are not evenly distributed. The high latitudes, which are near the poles, either the southern high latitudes down here or the northern high latitudes up here, are actually experiencing the most warming over the surface of the Earth from the 1950s to 1980s, as recorded by surface temperature measuring programs around the Earth. This has a potentially dire consequence in that a vast majority of a vast reservoir of water exists in these high latitudes, especially in the southern high latitudes where the Antarctic ice sheets represent or contain enough water to basically change sea level by roughly 70 meters. So if it's unlikely that the entire West Antarctic ice sheet and the entire East Antarctic ice sheet could melt due to the fact that the Arctic circumpolar current is kind of a feedback mechanism that supports their existence. But if they were hypothetically to melt, sea level would rise, not equally around the Earth due to gravitational and tidal forces, but sea level could rise up to 70 meters. Several organizations are working hard to understand climate change, both on local and regional and global scales. The Intergovernmental Panel on Climate Change, which is a UN-supported collection of thousands of research scientists who try to summarize and come to broad, useful conclusions that societies, that governments can use to make decisions on how they deal with climate change, has been in existence for a couple decades, and they release reports fairly often. They are a very dynamic active group. They have made projections that are pretty grim. On the right-hand side, we look at global surface warming as projected by the Intergovernmental Panel on Climate Change, which fundamentally, again, a lot of times in the news on particular radio stations or news channels, you'll see these organizations dismissed as biased and prone to dishonesty, but most reasonable people agree that there's nothing to that whatsoever. Again, politics and culture seem to influence people's judgment more than reality in this regard. But you can see that these projections are quite dire. This orange line is actually a projection for if carbon dioxide concentrations in the atmosphere were to basically remain as they are today. This would be the average global temperature increase over the next 80 years. It would still increase because there's enough inertia in the system that it will still go. But various emission scenarios with their uncertainties, which are the kind of the light color shades around these lines, vary anywhere from 1.5 degrees to 4 degrees of warming by the end of this century. Trace gases in the atmosphere, methane, nitrous oxide, and chlorofluorocarbons, which are CFCs, have a dramatic impact on global climate. They absorb wavelengths of Earth's outgoing radiation, just like carbon dioxide. Those are also greenhouse gases. Taken together, their warming effects may be nearly as great as carbon dioxide. So carbon dioxide and fossil fuel emissions are not the only problem here. There are a lot of other products of human as well as natural processes that may complicate climate change. And there are also climate feedback mechanisms that are sometimes well understood and others are poorly understood, that can either reinforce initial climate changes or can act against and remediate it. So those are zones of intense research focus among scientists at this point in time. Albedo, ice albedo is one of the major things, as ice, which tends to be surface ice, which tends to be white and reflective, tends to bounce a lot of light or a lot of solar energy back out into space. Seawater, on the other hand, is dark and tends to absorb a lot of heat energy. As ice melts, less energy, less solar energy is bounced back out into space, and things tend to warm faster. So as ice melts, as sea ice melts, you tend to warm those environments faster than you otherwise would, as if there were the ice mirror still there in place. Consequences of global warming are numerous. Or consequences of climate change are numerous. Nobody can absolutely predict the future, but we do know that as climate changes, weather patterns, climatology changes, weather tends to change, because weather is, after all, the manifestation of climate. Altered distribution of world's water resources can affect agriculture or worldwide. Can affect zones that depend on water for not only energy and agriculture, but for food. Rise in global mean sea level as water melts, or as ice, continental contained ice, that is Arctic sea ice, which is already in the water. If that melts, that actually doesn't change sea level. But continentally contained water, that is alpine glaciers and ice caps, as those disappear, as they disappear, I guess, or if they disappear, that can cause a dramatic change in sea level, which can affect low-lying areas much greater than areas of active tectonic, active margins where topography is much higher. And weather patterns can be affected as well. That is, intensity of hurricanes, tornadoes, extreme storms, drought, and heat wave. So that's it for chapter 20. Kind of a dire end to chapter 20. The next unit is unit 7, astronomy. Remember to take your quiz for unit 6. And thanks for taking the time to sit through all these lectures.